All right, friends and neighbors, welcome back. We are in chapter 26 of the CCNA study guides. And in this chapter, we're tackling IPv6 addressing and subnetting. So in this video, as always, we'll do the key topics. Our exam section is the network fundamentals still, configure and verify IPv6 addressing and prefixes. We're going to work on one particular set of addresses, the global unique addressing. Actually, it's the global unicast address and the unique local unicast address. And this time out, we'll do a demo for not only the global unicast space, but also a subnetted example. And then we'll follow that with the do I know this already questions. So the key topics from the study guide are the two types of IPv6 unicast addresses. We'll talk about the hex digits. So most of the IPv6 addressing that we deal with, you can tell the difference between them by just looking at the first couple of hex digits. We'll show a table later on for that, and we'll do several examples. And then, like IPv4, right, we did a lot on CIDR and subnetting and supernetting and variable length subnet masks. Turns out you can do the same stuff with IPv6 addresses, and you get used to looking at a particular section in IPv4. We're going to do the exact same thing here, but the masks are much, much longer. We'll go over some basic rules about how to find the subnet IDs, or at least identify the section that will allow us to figure out what the subnet ID is. And that'll be based on some global prefix that we have and then the prefix length that we have. We're also going to talk just briefly about some of the RFCs associated with this, and we'll talk about the rules for building unique local unicast addresses. Turns out they're written down in an RFC for us. And we'll wrap up with a quick comment on the subnetting rules for unique local. It turns out that they're very similar to the global unicast addressing. Now, if we think back to all the planning that went into the IPv4 address space, we had all those classes, and the idea was that each organization or company would get its own class of address, A, B, or C, depending on the size of the organization. For example, RIT has a class B network. But as more and more people joined the party, we realized that we were out of address space, and so we just couldn't do that. And so along came CIDR, which helped, and network address translation with its private addressing. Now, both approaches, whether you got your own globally unique address space, like one of the classes defined at IANA, your RIR, or you did private addressing with network address translation, you could do all kinds of subnetting throughout your network, right? It didn't matter whether you were private or public address space. Well, it turns out that the similar idea exists in IPv6. You can have globally unique address space, and you can subnet that up to your heart's content, or you can have a unique local prefix and then subnet that to your heart's content. The only difference is that unique local addresses also work with network address translation. Now, we can also kind of call the unique local address sort of private addressing. So the thing that we have to remember here, or be clear about, is that global unicast is unique to a company. And unique local should be unique to a company, but people can use whatever they want because, of course, network address translation. But the idea in RFC 4193 is that you would actually register what your unique local prefix would be, and then nobody else will use it. And we'll talk a little bit more about this, but it makes the idea of company mergers or things like that a little bit easier if you're not reusing the same space that somebody else is. All right, so first let's talk about the global routing prefix, or your globally unique address space. Well, just like in IPv4, IANA determines what addresses are out there and where they're going to be assigned. And so there's a geographic part to our IPv4 addressing. So a company would be in North America, for example, and Aaron would give out a chunk of address space after being assigned an address space or a big swath of the IPv4 address space from IANA. So the pecking order goes like this: IANA at the top, Then the regional internet registries, ARIN is the example for North America, and then the ISPs, and then the companies or the customers. Now, no matter what you got for your global routing prefix, that is the network that was assigned to you in IPv4, you could subnet it any way you wanted to. Well, the same thing is true with IPv6. So, IANA determines the IPv6 address space and the allocations. The RIRs are given their chunk of address space. They give it out to the ISPs, and then they give it out to the customers. So this is called your global routing prefix. And nobody else has the same prefix that you do. So the example in the book is that IANA gave to ARIN, the regional internet registry, the address space allocation of 2001::16, or I should say /16. There we go, fixed. So it's an enormous chunk of address space that's given to ARIN. ARIN then doles out this massive chunk of address space to the North American ISPs. And so one ISP might get the address space 2001:0DB8::32, which is a chunk of the address space within the larger /16. And then that ISP would give out a smaller chunk of that same address space to a company or a customer. So in this example, it's 2001:0DB8:1111/48. And so at each one of these steps, there's 16 bits of address space that is allocated to whatever the next layer down is. So that would be the global routing prefix, and the addresses that are contained in there are the global unicast addresses. So these are unique. They're part of the public address space for IPv6. Now, the global unicast addresses take up the lion's share of the IPv6 address space. There are a couple of other allocations here you can see in the table. But the global unicast addresses all begin with 2000::3. Now remember, the 3 is just how many bits are in the mask. So there would be 3 bits in this mask. And so it would be 1110 in the first hex character in the mask. Which also means that this result could be either a 2 or a 3 in that first hexadecimal character. Now we already know that IPv6 is sort of outlined in RFC 8200. RFC 4291 has the IPv6 addressing architecture that describes all of the different kinds of addresses that are in use. Other IPv6 address values include, we've already got the global unicast, which is what we're talking about right now. Unique local unicast, those begin with FD, or Foxtrot Delta. Any multicast address in IPv6 begins with FF. And then linked local addresses, addresses that you're going to use on this network, begin with FE80. So those are dead giveaways of the kind of address that you're dealing with. But for right now, since we're talking about the global unicast addressing, all of the addresses that we talk about will begin with 2000 in something. So our examples are going to be 2001. So let's take a quick look at a demo for how these might be assigned. So let's take a minute to take this in. We have 4 IPv6 networks. Right up here we've got the 2001:0DB8:1111/48. So that means that all that we care about is these first 3 quartets, or 3 16-bit chunks, 48 bits of the address space. Down below we've got 2001:0DB8:2222, and then 2001:0DB8:3333. So those are the 3 networks that I configured on the left-hand side. Connecting all of those is the 2001:0DB8:4444:0/64. And I did that just to show you that you can mix and match these masks or these prefix lengths in the same way that you could in IPv4. So let's take a look at an example of one router here. And the first thing that we'll do is we'll take a look at some of the commands that we issued here. Now the first up is in the interfaces themselves. You can see that we have no IP address here, but that's of course because we're using an IPv6 address. That's actually the syntax for the command, IPv6 address, and then whatever you're going to do. And you can see that I've assigned a host address, but the mask associated with this network is a /48. That means this host lives within this massive address space of /48. On the other side, I've defined a different network, and we'll see that several of the routers are going to share this address space. So if I take a look at my IPv6 routing table, we're just going to do a show IPv6 route. We can see that I've got two directly connected networks, right? We have the 1111 network and the 4444 network. And then look at these crazy masks here. Well, these identify the IP addresses of the interfaces right there. Now in IPv6, we'll see an entry that looks like this. These are for the multicast addresses. In an IPv4 routing table, you would see a 224 in there. Here is the IPv6 version of the multicast. Now our router 3 is a little bit different because it needs static routes to all of the destination networks. So I've only given one address here, right, to this particular router. So it's part of the 4net or the 4444 network. But in order to get to the 1111, the 2222, and the 3333 networks, we need static routes. And so this is no different than the IPv4 static route, right? We would do IP route and then the destination network followed by the mask followed by the forwarding router's interface. It's the same thing here, except it's an IPv6 route. Here's the destination networks that I would like to get to, followed by the forwarding router's IP address, which just happens to be an IP address. So the last thing that we'll look at here is the routing table for this router. And we can see we've got one directly connected network along with the interface identifier, right? And then all of these static routes. Notice that the administrative distance is exactly the same as we're used to seeing in an IPv4 network. Well, there we go. So that's how you would build a very, very small router topology. We'll spend more on these in Chapter 27. So we just looked at some global unicast prefixes or some unique global prefixes. What if I'm given a global unicast prefix and I want to subnet things now? Well, it's going to be the exact same kind of thing, but we're getting used to these large masks and weird looking IP addresses. Subnetting a global unicast address space is much the same that you've done before, but it might actually be a little bit easier because we get to know and love just a couple of masks. It's not quite as crazy as the subnetting that you've done before. So in the examples that we've done so far, you saw that our global prefixes or our global routing prefix was a /48. And then if we say, well, the host portion is going to be 64 bits, then our subnet space is all inside that 16 bits in the middle. So most RFCs say use /64 for all the subnets. So the prefix length for a subnet will almost always be 64. But again, if your global routing prefix is /48, all your subnetting is right inside that one quartet of 16 bits. Now, just because we're in IPv6 doesn't mean we change any other rules, right? If you assigned previously an IPv4 subnet to a VLAN, you do the same thing with IPv6. So the rules are the same, right? We have hosts on the network. We have a default gateway on the network. We put all of them in the same VLAN, right? So those rules are still the same. Now, there is a design question here. How many subnets do you need? How many hosts per subnet? Now, with IPv6, the number of hosts is going to be enormous, right? But if we just say, oh, okay, they're all /64s, then the real question is how many do we need to create, and what would be those subnet IDs? What would be the mask used with your subnet IDs? Now the book example is the one that's on the bottom of this slide. We have 2 to the 16th possible subnets. Well, what does that mean? Remember that these are hex characters. So here is our global routing prefix. So 2001 0db8 1111 /48. If the host portion, the host interface portion, is /64, right? We've got 1, 2, 3, 4 16-bit quartets. That's 64 bits of addressing space for hosts. The remaining portion is right here in the middle. These are not binary zeros, they're hexadecimal zeros, which means that you have 16 bits. So 2 to the 16th possible subnets inside this global routing prefix, and each one of them will have 64 bits of addressing for hosts. Okay, so how would we subnet a global unicast chunk of address space? How would we subnet the global routing prefix? Let's take a look at another example. So if we take a look at what we have here, we have what looks to be one IPv6 network, but that's not what's going on. Here we have the 2001 DB8 1111:1/64. Here we have the same address space, but it's :2, and here we have :3. So that means that we have designated the 1, 2, and 3 portions of this address space as part of the prefix. Now, each one of these has 64 bits of addressing for the hosts. And so that means that the subnet portion is this 1 right here, the 2 right there, the 3. So the 2001 DB8 1111:1, that's a subnet. The :2, that's a subnet. The :3, that's a subnet. So what you're actually looking at here is 3 networks. Now, just like in IPv4, if I take a look at from the perspective of router 6, it would be directly connected to the 1 and the 2 subnets, and would have to have a static route to get to the 3 network. Router 7 would be directly connected to the 2 and 3 subnets, but would need a static route to get to the 1 network. Well, let's see what that looks like. I think I forgot to mention this earlier. We've turned on IPv6 unicast routing. And then here are our 2 interfaces that are connected to the networks. Here we have 2001 DB8 1111. Notice the 0 suppression that I've done here, right? No 0 here, no 0 here. Same with the labels. And here we have the 2 subnet. Now, how do we get to the 3? Well, here it is. I want to get to the 3 subnet /64, right? That serves as our mask. How do I get there? Well, it has to be somebody that's not me, but somebody that I can reach out and touch on the 2 network. So 2.254. Remember that my address on the 2 subnet is .253 or :253. Well, let's take a quick look at that routing table. And here we have it. Directly connected to the 1 subnet, directly connected to the 2 subnet, and I have a static route to get to the 3 subnet via 2:254. Now I also have a couple of hosts out here. Now the host addressing might be a little confusing. Hopefully you can see this. But here my host address is 1111:1 for the subnet, and then ::1 for the IP address, the last octet. /64 is the mask here, and then I've got a default gateway in the same way that I have in any other IP address or IPv4 network, right? We do the exact same thing. So I had to do the same thing over here just for fun. Let's see if this works. So you can see that I got it to work before, but there we have it. We're pinging. If we were to do the simulation, here goes ICMP version 6. There's our RFC 4443 popping up. So it goes all the way across with our routing. There we have it. So ping version 6 and the response. All right, that'll do it for this particular demo. Well, IPv6 subnetting using unique local addresses. So we just did global unicast addresses with a global routing prefix. What's that unique local, right? These were also supposed to be globally unique, but they were private. So unique locals act as a private IPv6 unicast address. They should be unique, not locally created. Now that doesn't mean that you can't, right? You can use anything that you want for unique local addresses, but the author of the CCNA text and the RFCs also state that, well, you ought to pick an address that is based on the rules in the RFCs and also register that so that nobody else uses your private address space. Now the subnetting works exactly the same as the global unicast, but the difference is that when you're looking at the address, instead of beginning with a 2 or a 3, it begins with FD. So there is a strategy here with choosing a unique local, right? If we were going to pay attention to the RFC and the naming or the numbering convention, you just automatically start with FD or Foxtrot Delta in the very first 2 hexadecimal spots. Then you choose a 40-bit global ID. This is what would be unique. Now I've got it in red for a very particular reason. It's important to remember that this is the global ID for unique local addressing. When you add FD to it, that's another 8 bits, so you get 48 bits, which is our standard size for an IPv6 initial prefix length. We get the same 16 bits for subnetting that we just saw used in global unique or global unicast addressing. Now the chapter points out that technically in the RFCs there's a definition beginning with Foxtrot Charlie or FC, but RFC 4193 specifies that the 8th bit should be a 1. So if you turn that 8th bit to a 1, that actually makes this Foxtrot Delta or FD. Well, let's take a quick look at those RFCs so you can know what I've been talking about. First up here is RFC 4291, the IPv6 addresses, and I've just got one example here. So if you want to take a look at how the addresses are structured, take a look at RFC 4291 and you'll see that they're all defined here, right? All of these address types. And RFC 4193 has the instructions for creating the unique local. And this is a suggested sample code for the pseudo-random generator. Now, once you would get your global ID for your unique local, you would register that so nobody else would use it. But here we have it, right? To obtain the time of day and so on. But you can read this particular process or procedure out there in the available RFCs. All right, time for the do you know this already questions. Which of the following IPv6 addresses appears to be a unique local unicast based on the first few hex digits? Well, now we know that unique local addresses begin with FD. And so that was the answer Charlie there, or C. Which of the following IPv6 addresses appears to be a global unicast based on the first few hex digits? You're seeing a theme here, right? If you look at the first couple of hex digits, you know what class of address they're going to be or what type of address. The same was true for IPv4. Class A, B, and C had a very particular range of addresses. In this particular case, the global unicast is A, beginning with 3123, right? It begins with a 2 or 3, that's global unicast. Question number 3, when subnetting an IPv6 address block, an engineer shows a diagram or a drawing that breaks the address structure into 3 pieces. Comparing this concept to a 3-part IPv4 address structure, which part of the IPv6 address structure is most like the IPv4 network part of the address? Well, the network was the prefix, and so in IPv6, the answer was D, the global routing prefix. Question number 4, when subnetting an IPv6 address block, an engineer shows a drawing that breaks the address structure into 3 pieces. Once again, assuming that all subnets use the same /64 prefix length, Which of the following answers lists the field's name on the far right of the address? That's 64 bits of address space for host. That's called the interface ID. For the following IPv6 address, which part of the address is considered the global ID of the unique local? Well, that was why I had that in red in the earlier part of this presentation. So the part beginning after Foxtrot Delta, after FD, that is the global part of the prefix. So 00, 1, 2, 3, 4, 5, 6, 7, 8, right? So that 40-bit chunk is the global ID for the unique local address. Whew, that is a mouthful. All right, the chapter 27, look ahead. We are going to take a look at IPv6 addressing on routers. We did a little bit today. We did a little bit, but we didn't really build a whole lot. So what we did today was also static unicast. We're also going to look at something called an EUI64 formatted address, dynamic unicast, along with DHCP discussion, and special addresses. Now, at this point, I'm going to remind you that I've done an IPv6 series where I go from an IPv4 network build step by step through an IPv6 network build all the way down to the host, and I'll link those in the show notes. Well, oh yeah, this has been IPv6 addressing in subnets. Today we talked about the global unicast and unique local unicast. Both of them have a global ID associated with them. One is public and one is private. So global unicast gives you a global routing prefix that is registered and it is public. You should register your unique local prefix as well, although technically you don't have to because it's private. It's going to be behind a NAT box. We also looked at how to subnet these two kinds of address space. We looked at some routing tables and we did some demos, right? They were quick, but we're going to do lots more. Well, like and subscribe for IPv6 and routers. And whether you're using global unicast or unique local unicast, may those packets always reach their destinations. And we're doing CCNA, you're doing CCNA, you can do this.